Okay, so imagine using AI not just to like sort through tons of data, but to actually solve like a real, scientific problem.
Yeah.
A puzzle that's been like bugging physicists for like decades.
Yeah.
It sounds kind of like sci-fi, right?
Yeah, it does sound like sci-fi.
But it's happening like right now, and it's revealing some pretty incredible secrets about how materials behave at like the most fundamental level.
I think what's so fascinating about it is how AI is allowing us to tackle problems that were previously beyond our reach, even with like the best tools we had, especially in fields like condensed matter physics.
Exactly, and that's what we're diving into today. The exact solution of the 1DJ, 1J2 Q-state POTS model with next nearest neighbor interactions.
All right.
Now, if you're like new to this area, think of it as like a notoriously hard problem in statistical mechanics, like a real intellectual Everest that researchers have been trying to like climb for years.
Mm-hmm. Yeah. And, for those of you interested in AI and ML, this research is a demonstration of AI acting like a reasoning engine, moving beyond just pattern recognition and actually contributing to major theoretical breakthroughs.
And that has, big implications for how we understand and model complex systems, from materials to even biological processes.
Absolutely.
The source for our deep dive today is this paper, Exact Solution of the Frustrated POTS Model with Next Nearest Neighbor Interactions in One Dimension, an AI-aided discovery by Weigo Yin, dated April 1st, 2025, from Brookhaven National Laboratory.
Okay.
And the really exciting part is that AI, specifically OpenAI's O3 mini high model, played a key role in getting that exact solution for the Q equals 3 case, which then led to a general solution that works for any Q value.
So how did AI, which we usually think of as processing information and finding correlations, become such a vital tool in solving a fundamental problem in theoretical physics? That's what's so groundbreaking about this.
Yeah, so our mission today is to unpack this research. We want to understand what this J1, J2 Q-state POTS model is all about, why it's been so hard to solve analytically, what role the AI played in cracking it, and what these findings mean for the broader scientific community, and maybe even for fields like AI itself. Mm-hmm. And we're going to break it all down in a way that's easy to understand, even if you're just starting to explore AI and scientific discovery.
Sounds good.
Okay, so first things first. What exactly is this J1, J2 Q-state POTS model?
At its core, it's what we call a spin model in physics. Now, for someone interested in AI or ML, you can think of it as a way to represent the magnetic properties of materials at the atomic level.
Okay.
So each atom is represented by a spin, which can exist in a certain number of states, and you can think of these spin states as being similar to categories or classes that a variable can take in a classification model.
So instead of just like an up or down state, like in the simpler Ising model where Q equals 2, the Q-state POTS model expands that to Q possible states. The paper says that this kind of bridges the gap between systems with discrete symmetries like the Ising model and those with continuous symmetries like the Heisenberg model. What does that actually mean?
Well, by increasing Q, the POTS model becomes more flexible in representing the kinds of order you see in real materials. So the Ising model is great for understanding ferromagnetism, where all the spins align, or anti-ferromagnetism, where spins alternate.
Right.
But many materials have more complex orders, and the POTS model with Q greater than 2 can capture that richer behavior.
Okay, so the J1, J2 part refers to the interactions between these spins, right?
Exactly.
We've got nearest neighbor interactions, J1, and next nearest neighbor interactions, J2. Can you kind of visualize that for us based on figure 1A in the paper?
Sure. So imagine you have a line of spins like beads on a string.
Okay.
The J1 interaction is like a spring connecting each spin to the spin immediately to its left and right, its nearest neighbors. Got it.
Now J2 is like a longer spring connecting each spin to the spin that's 2 positions away.
Okay.
Equation 1 in the paper, which is the Hamiltonian, provides a mathematical description of the energy of these interactions depending on whether the spins are in the same or different states.
And the paper talks about this concept of frustration when J1 is negative.
Yeah.
What's that about? The material isn't actually getting frustrated, is it?
No, not in the way we understand it.
Okay.
Frustration here means the J1 and J2 interactions are in competition.
Okay.
So if J1 prefers neighboring spins to be in opposite states, but J2 wants spins 2 positions apart to be in the same state, these conflicting wants create frustration. It can't satisfy both at the same time, which leads to more complex ground states. So the paper gives some real-world examples where this 1DJ, 1J2 POTS model could be relevant. We're talking about layered materials, charge stripe ordering in compounds, like law 1.67 senior 0.33 in the nerve, 4 the Star of David charge density wave, and 1 T-terrace, 2 spin spiral ordering, and UR2 and even table tennis training drills.
Right.
Table tennis, that's kind of out there.
Yeah, it's a cool example of how these abstract math models can show up in unexpected places. In table tennis, you could think of the player's choices at each step as the states in a POTS model, and the J1 and J2 interactions could represent the influence of previous moves.
Okay.
But as the paper says, the main use of this model is in understanding how complex materials behave at the atomic and electronic levels.
So we have this model with competing interactions between spins that can be in multiple states. Why has finding an exact solution for this model, especially for any Q, been so hard for scientists?
The main problem is the transfer matrix method, which is the primary technique to solve these models. You basically build a matrix that describes how the system evolves from one step to the next. And the size of this matrix grows incredibly fast with a number of states, or Q. Specifically for this 1DJ, 1J2 POTS model, the rank of the matrix is Q squared.
Q squared. So even if Q is just 3, we're talking about a 9 by 9 matrix, which isn't that big computationally, but the paper says it's tough to solve analytically, meaning with equations and derivations.
Exactly. Analytically means by hand, basically.
Right.
A 9 by 9 matrix is already complex algebraically.
Right.
Now imagine if Q gets bigger, like 10 to the power of 10 to the power of 10. Diagonalizing a matrix that big, even with supercomputers, is impossible. That rapid increase in complexity is why getting a general exact solution has been so elusive. And even the seemingly simple Q equals 3 case is different from the Q equals 2 or Ising model. So solving it was a big step.
Yeah, it's amazing that only the 1J2 Ising model with Q equals 2 had been solved exactly before this. So how did AI help overcome this? The paper mentions 2 recent developments.
Right. The first one involves research on decorated Ising ladders, which are slightly more complex arrangements of spins. And they found something called ultra-narrow phase crossover, or UNPC.
Okay.
This work used something called symmetry-based block diagonalization to simplify the 4x4 matrix down to a 2x2 matrix.
All right.
The significance here is that we might be able to use these 1D frustrated magnets at finite temperatures.
So that's one piece of the puzzle, using symmetry to make the math easier. What's the second development, the one that inspired this work?
The second one happened at a scientific jam session where OpenAI's O3 mini-high model came up with an equation for the critical temperature of UNPC in these Ising models. The author of this POTS model paper was there and saw the AI reasoning and deriving this result, which gave him an idea. Could a similar method be used to tackle the Q equals 3 POTS model?
That's incredible. So the AI wasn't just analyzing data, it was finding new results. So how did the author use this to solve the Q equals 3 case?
He started by giving the O3 mini-high model information about the Q equals 3 system. Now, the AI didn't always get it right. There were errors and wrong suggestions.
Okay.
But by giving it prompts, looking at the output, and refining the questions, the AI eventually found a symmetry-based block diagonalization that reduced the 9 by 9 matrix for the Q equals 3 POTS model down to a 2 by 2 matrix.
Wow, from a 9 by 9 down to a 2 by 2. That's a huge simplification.
Exactly. And this success with Q equals 3 led to the general solution for any Q. The key insight was the full permutation symmetry of the Q-POT states, meaning the Hamiltonian and the transfer matrix don't change no matter how you label the states. The term for this is the symmetric group, SQ.
So the AI couldn't generalize from the Q equals 3 solution to any Q. It even warned about the growing number of permutations, but the fact that both the Q equals 2 and the AI Q equals 3 cases led to a 2 by 2 matrix hinted at something deeper. What was that?
The author realized that when the system is infinitely large, only the largest eigenvalue of the transfer matrix matters. So the goal became finding the subspace containing this eigenvalue.
And they found that this subspace is spanned by just 2 maximally symmetric vectors, right? Equation 3 in the paper. What do these vectors mean in terms of the spins?
Think about how the spins are arranged. One vector, chess, represents all neighboring spin pairs being in the same state. It doesn't matter which of the key states it is, it's symmetrical. The other vector test represents neighboring pairs being in different states. Again, it's symmetrical because it doesn't depend on the specific pairs. Since all elements of the transfer matrix are positive, the largest eigenvalue is guaranteed to be in this 2-dimensional subspace.
So by focusing on this 2-dimensional subspace, the huge Q-squared dimensional transfer matrix T could be projected onto a much smaller 2 by 2 block T2 right. Equation 4.
Exactly. The UQ2 matrix acts as a projector, isolating the part of the matrix that governs the largest eigenvalue. And because of the system's symmetry, this T2 block is separate from the rest. It can be analyzed on its own.
And from this 2x2 matrix with its components UV and W defined in equation 5, they got the exact solution for equation 6, right?
That's right. The expressions for UV and W are just combinations of the inverse temperature and the interaction strengths J1 and J2. And because they focused on the symmetric subspace, these expressions were found without dealing with the huge full matrix. And once you have the largest eigenvalue, you can calculate the system's properties like free energy entropy and correlations.
Okay, so what insights into the physical phenomena did this solution reveal? Figure 2 shows the Q-dependent phase diagrams. What stands out to you?
One thing is the appearance and disappearance of a TC dome-like phase at low temperatures. For smaller Q, you see the dome. But as Q gets large, like 10 to the 6, it vanishes. This relates to how atomic or electronic orders stack in layered materials. The number of internal states Q determines which phases are stable under different temperatures and interaction strengths.
What about at absolute zero? The paper says there are 3 phases separated by 2 critical points for all Q.
Yes, at zero temperature, you always have 3 phases depending on J1. When J1 is large and positive, you get a ferromagnetic phase where all spins align. For Q3 or greater, the middle phase is a randomly dimerized state, or RDS, and for negative J1, it's a paramagnetic phase.
The paper mentions some differences between Q equals 2 and Q greater than or equal to 3, particularly about the critical points and residual entropy. What's that about?
For the Ising model, the critical points are at plus or minus 2. None of the phases have macroscopic degeneracy, meaning there's only one ground state at zero temperature. But for Q3 or greater, the critical points shift to 0 and 2. And both the RDS and paramagnetic phases have residual entropy. This means even at absolute zero, there's some disorder, with many configurations having the same minimal energy.
The paper links the RDS and its entropy to the Star of David charge density wave in 1 TT-S2. What's the connection there?
The Star of David is a complex arrangement of electrons. The residual entropy in the RDS suggests a similar disorder, where many configurations have the same energy. The Q-1 choices for the next dimer in the RDS relate to the degeneracy in the Star of David structure.
And the paramagnetic phase with negative J1 also has residual entropy for Q3 or greater, except for Q equals 3 where it's 0. The paper mentions ABC stacking and spin spiral order here.
Right. For Q3 or greater, each spin has Q-2 choices to be different from its neighbors, leading to entropy. But when Q is 3, there's only one choice to maintain the lowest energy. This creates a repeating pattern, like 1, 2, 3, 1, 2, 3, and so on. This has a unique ground state and 0 entropy. It's similar to ABC stacking in crystals and the 120-degree spin spiral order in UASB.
So these residual entropies at the critical points seem important for the TC dome. Figure 3 shows the entropy at 0 temperature versus Q. What's the connection?
Figure 3 shows that for small Q, the residual entropies at the critical points are larger than the RDS entropy. As temperature rises, the system explores these high entropy states, creating the V-shapes in the phase diagram. When these V-shapes merge, they form the TC dome. So the dome's height and size are determined by the entropies at the critical points.
So the TC dome's appearance and disappearance as Q changes is explained by how the entropies at the RDS boundaries change with Q.
It's exactly. For larger Q, the entropies at the critical points are similar to the adjacent phases. So as temperature changes, the system is more likely to transition to the adjacent phase, and the V-shapes and TKC dome become less prominent or disappear.
The paper connects this to the TSI dome in unconventional superconductors, suggesting it offers a mechanism for its formation. That's a pretty big deal.
It is. The TSI dome is common in unconventional superconductors, and its origin is still debated. This research offers a new idea that the dome comes from competing interactions and entropy at the critical points, with the number of states Q playing a key role.
This research really shows how AI is becoming a tool for scientific discovery. The paper calls it data and value-driven discovery. What does that mean here?
It means AI isn't just analyzing data, it's generating insights and helping solve problems. Here, the value was the exact solution for Q equals 3, which the AI helped find. This then led to the general solution by highlighting symmetry.
And while the AI made mistakes, it couldn't generalize the solution alone. Its contribution was crucial, especially for the Q equals 3 case.
Definitely. The AI's ability to do symbolic math, even with some errors, and its insight in finding the block diagonalization were key. The fact that it could make Wolfram Mathematica code shows its potential as a tool, but the general solution still needed human intuition and ingenuity to use symmetry.
So to recap, for those interested in AI, ML, and physics, this shows how AI can go beyond pattern recognition and help solve theoretical problems leading to the exact solution of the 1DJ, 1J2 Q-state Potts model. Symmetry was key. The model has various phases, and the TC dome for small q offers insights into materials and maybe superconductivity. This highlights AI's growing potential as a reasoning partner in scientific discovery.
What's fascinating is that this is a new collaborative approach to research AI. Assists human scientists exploring complex math and generating insights that would be difficult or time-consuming for humans alone.
This deep dive into the Potts model solution shows how AI is unraveling the physical world. As AI evolves, what other mysteries will it solve? Could AI become essential for breakthroughs in many fields? This is a question worth thinking about. If you're interested in the details, check out the paper.
This research really opens up a lot of possibilities for AI and scientific inquiry.
It really does.
Yeah.
Thank you so much for joining us.
Thank you.
It was great having you here today to go through all this.
My pleasure.
And to all of you listening out there, we'll catch you in the next deep dive.
Take care.
Bye.